Welcome to our talk about life or death. I think we have to go away from the speakers. Life or death of a Kubernetes request, API request. I'm Stefan Schimanski, working on API server since ages, 10 years or something. Have touched a lot of the things we will show here. And I have with me Abu.
I'm a software engineer at Red Hat.
And a similar history about API servers. So what we want to do today, we want to talk about API requests, obviously. But imagine you are sitting in this interview, right? You want to apply for a job, or you're applying, and there's this interviewer next to you, and a very common question is, and you will maybe experience something in a similar context. API server is, of course, a topic, but you get asked, so you do that, right? You type kubectl create --v9 and pass some manifest, and what happens, right? You press enter, what happens? That's the question. And we are all in that interview situation now, so we want to talk about the interesting bits of the API server and kubectl. What happens if we do that? And not everything is new, so there was a old talk from Daniel Smith years ago, many years ago, I'm not sure, maybe 8 years ago or so, with a similar title. But of course, Kube has changed, has become much more complex. And I bet 80% of the audience has joined the project after that talk, so will be lots of new stuff. Anyway, this is the start of the conversation here, and most of you will have done --v something, like 7, 8, 9, something this dimension, and you get logging, right? So you see the kubectl does something, and in particular, it's doing the request, right? The request here, and this looks super innocent. You find the batch, the word batch, the word v1, and on the first view, you see job, right? But there's the first detail, which is super interesting. This is jobs, lowercase, plural, and this one is an uppercase word, singular. And this is already not trivial in Kubernetes, how this mapping actually happens. And of course, when the request is done, it's a post request to a URL, and there's a 201 returned, and this means success, so a batch is created. But everything in between we want to talk through now. So this mapping, you will have heard about kinds and resources in Kubernetes, and the kind is the one in the manifest, resource is the one in the API path here. They look different, but they don't have to be similar. They can be completely different words. And for example, this could be the job, and this could be elephants or something, right? There's no connection between them. So connection is done by discovery. There's discovery, the API server serves discovery, and kubectl will query that, which returns all resources with the kinds served under the resources and lots of other meta information. And in Kubernetes, we call that a REST mapping. REST mapping is, so kubectl takes the manifest, parses the YAML, passes out the kube version kind, so batch v1 job singular, and then REST mapping happens, and it has group version resource, and this is basically just the words, the terms here in the path, and it can do its request. But even here, something is happening, and this is REST mapping. And then the request is sent to the API server. So let's see what the API server does.
So our request is now making its way to the Go HTTP server that is basically listening to and serving all incoming HTTP requests. So this is rather a very simplistic view of what the HTTP server does when it accepts our request. In step 2 of the figure, you can see that it creates a new HTTP request object that represents our request on the server. It has the request parameters, the headers, and also the body that we provided. And then it creates a new response writer object that can be used to construct an HTTP response. It then invokes the user-provided handler with the request and the writer. So a handler is a user-provided function that is responsible for responding to the request. And it uses the writer object to construct the HTTP response. A little segue into a Go routine. So a Go routine is basically a lightweight thread managed by the Go runtime. This allows a Go application to have concurrently executing functions. So the question is, like, how does the HTTP server invoke the handler? Does it invoke it on a new Go routine? The answer depends on, if you look at the standard library implementation, for HTTP version 1, it executes the handler in the same Go routine. For HTTP version 2, the HTTP server executes the handler in a new Go routine. So the API server does not have like a single monolithic handler function that serves the entirety of the request. Rather, we have a chain of handler functions, each of which is responsible for like serving a certain aspect of the request, right? And the API server builds the handler chain when it starts. So this is a more comprehensive view of the handler chain we have. We have omitted some handlers for simplicity. So the request object has a context, and it has deadlines, it has cancellation signals, and also request scoped values. So a handler function can attach value to the request context. This enables like a future handler to access that value in order to serve the request. So when the first handler receives the request, the context is bare minimum. It has no deadline. It has a cancellation signal prepared by the HTTP server so that the server can abort the request on any error. As the request passes through the handler chain, the context gets populated with information like deadline, user information, so request information, and audit events. So the first stop at the panic recovery handler, it is responsible for managing panics thrown by a request handling code, right? This figure basically sketches out the path that, let's try this, the path that a panicking request takes. So we start at the Go HTTP server. It invokes the complete request handler in a new Go routine. And then at some point, the panic recovery handler starts executing, and then it takes the rest of the handler chain, and then it invokes it in the same Go routine. And this is the rightmost timeline, and we can see here the first panic. This is basically the request handling code unexpectedly panicking. And as the panicking Go routine unwinds, the panic recovery handler stops the panic, recovers the error. It also captures the stack trace. So we basically pinpoint the exact location where the panic originated from. And then it logs the error and the stack trace, and then it also panics here. And this is by design so that it can let the HTTP server decide what to do with the panic. So the HTTP server recovers from the panic. It also logs, and then it basically sends an error reply to the user. So how does a request that panics on the server, what does the client observe, and what also, like, how does it manifest on the server side, right? So what if the example request that we sent using kubectl, it panicked on the server? So if we used HTTP1, we would see an error like end of file. It's because the handler didn't have a chance to write any bytes to the response yet. We see unexpected end of file when the handler wrote some bytes to the writer, and then it panicked. But for HTTP2, we see a stream reset error with the internal error code. Now, these errors are not exclusively meant to communicate a panic, so they could be for other reasons too. So how do we distinguish? So we can look at the server logs, which will tell you that the request panicked. It also prints the request path for you, and on the audit ID. It also, you can see here the stack trace from the panic, so we can pinpoint the actual line that caused the panic. And the matching audit event, it has a reason, timeout error, and we can see 500. So this tells us that this request panicked on the server. I think it's you.
Yeah, the next part of the chain is parsing the request, so in a logical way, like understand the URL, the path of the URL, understanding certain parameters of the URL and the verbs in particular. And This is a very common struct if you look into API server code. Many parts of the, I lost the laser, it seems. No, it's back. So this request info is in the context, and you can always just ask for it, and you have the past logical structure of a request here. And the most interesting bit is probably the verb. And we use logical verbs in Kubernetes. So we have get, list, watch. But they actually are all get verbs for HTTP. The others map quite naturally. But yeah, those things are stored in the request info. And for our request here at hand, we have a create for a job in the batch group, and you will see the expected information. So batch v1, namespace is extracted, it's foo, it's jobs, and it's a resource request, so it's not something like metrics or healthy or something. It's a real quad operation, so that's why resource request is true. And you might, if you have written webhooks for admission, you will see similar values, which come basically from this struct. Requests also have a lifespan, and there are two kinds of requests. We call them long-running. Watches are long-running because they run at least half an hour or something, or maybe even longer. And if you do kubectl log, you will, and you follow the log, it never terminates at best, right? So it's a long request. And watch proxy are two verbs which we consider long-running, and we have some sub-resources which we consider long-running. But this is basically hard-coded in Kube API server. So if you write another API server behind an aggregated one, basically this is what you have, right? Those are long-running. Everything else is cut off eventually, and Abu will show in a second how this cutting off works, how timeouts work.
Yeah, so we have stopped at the latency tracking handler. So it tracks the latency incurred by an in-flight request at various layers within the API server, and it's recorded as annotations in the audit event, but we only record it when the request exceeds like a threshold of 500 milliseconds. Some of the fields, these list some of the audit annotations that we have today, and I can go through some of them. Like for example, the amount of time we spent in the authentication and the authorization phase. We also have like how much time the request spent in the mutating and the validating webhooks. This one is very interesting. etcd, it tracks the latency incurred at the storage layer. And usually a single request may involve multiple round trips to etcd. So this shows the total amount of time the request spends in the storage layer. We also have latency tracker for how long it took us to serialize the request, and also how long it took to write to the response writer object, right? So this could be a very helpful tool for debugging like cluster issues. For example, if you have the audit ID, and if you are looking at, if the customer is complaining about like slow API, you could actually look at these audit annotations, and it would give you some clues as to what's going on under the hood. Next. The next one is the HTTP log handler. It prints attributes of all the incoming requests. It's only available if you run the API server at log level 3 or more. But the interesting thing is, if you look at the kubectl log, it prints the audit ID, which represents the request. And if we take the audit ID and grab for it in the API server log, we can find a matching HTTP log entry, which shows the request path and also the status code that it returned and how much time it took to execute. So this also can be very like a tool that can aid in cluster debugging. Okay. Now our request has made it to the deadline handler. So this handler allocates a deadline to non-long-running requests, and it attaches it to the request context. So if the client doesn't specify a timeout for the request, the handler will use a default of 60 seconds today, and a cluster admin can optionally override this value through the request timeout command line option of the API server. So what happens? What if we wanted to specify timeout for our request? So here we can actually use the option provided by kubectl, request timeout, and we're saying that the request should complete within 30 seconds. So our handler will basically use 30 seconds as the deadline for this request. Okay. So next is the timeout handler. So why do you need a timeout handler? So like the request handling code may not respect the deadline in the context, right? So we need a timeout. The timeout handler is basically responsible for enforcing the timeout. So this diagram shows, in red, it shows the path that a request takes when it times out. So if you go through the events, and they're already listed chronologically, so the Go HTTP server takes the complete handler chain, and it executes in a new Go routine, and that's the Go routine A we see here. And then the handler chain executes, and then we have the timeout handler here. It takes the rest of the handler chain, and then it executes it in a separate Go routine here. And then it waits for the handler chain to return for 30 seconds. Like, it will wait at most for 30 seconds. So what happens here, this handler chain is executing, and it's taking more than 30 seconds. That's D1 in this diagram, right? So the timeout handler then will not wait for it any further because the deadline has exceeded. And then it basically prepares a timeout response for this request. And then it returns, and then the Go HTTP server takes control, and then it returns the reply to the user. So that's how the timeout handler works within the Kube API server. So it is necessary because sometimes the client doesn't have any timeout, and if we don't have a timeout enforcer in the API server, the client could hang indefinitely, and that's not something we want. So what if we had, we had our request to timeout? So we can choose a timeout value that is long enough that kubectl will send the request to the server, but then it will immediately abort with a context deadline error. So I was able to do that with a timeout of, you can see here, 6 milliseconds, right? And then it's short enough that on the server, it will not be able to finish in time. And then if you look at the server logs, we can see that the matching HTTP log entry shows that it basically timed out, which is 504, gateway timeout. And then if you look at the matching audit event, it will tell you that the request timed out, it's 504. So like if you have an audit IDs that you are debugging cluster with, you can just, this information could be very useful. So the next stop is the priority and fairness handler. So API priority and fairness is a self-defense mechanism of the API server. It regulates the load on the server, and it uses like a fair queuing algorithm to schedule the requests. So when our request enters the filter, the handler, we have here the classifier. Basically, it finds a matching flow for our request, and then it uses shuffle sharding to select a queue, and then the request gets put into this queue, and then the request basically goes into a waiting state. And we have a scheduler in the priority and fairness that asynchronously decides on the request. If the decision is accept, the request, basically the rest of the handler chain gets executed. Otherwise, like the request waits in the queue. So the question is, how long do we allow the request to stay in the queue? The answer today is 1/4 of its allotted deadline. And then once the deadline exceeds, the scheduler will remove the request from the queue, and it will send a reject reply to the user. And today, the reject reply looks like it has a status code of 429, and then it will have in the response, it will have a header called retry after. It will have a value n. This represents the number of seconds the client should wait before it retries. Okay. So what if we get our request to get rejected by priority and fairness? So this is what we'll see in the log. We can see that, oh man. In the response, you can see it's 429, which indicates too many requests. And it sees a retry after header in the response, which has 1. That means it should wait 1 second before the next retry. And that's what kubectl logs here. And it keeps retrying, and then if within the retry parameter, if it succeeds, otherwise it fails, right? And then there's a very interesting observation here. This server processing milliseconds, it shows 1,500 here. So it's, sorry, 15,000. So it is equal to 15 seconds. So could it be that the request waited in the queue for 15 seconds? Because if you notice here, when we did kubectl create, we didn't specify any timeout. And the default is 60 seconds today. And 1/4 of that is 15 seconds. So it could be that the request waited in the queue for 15 seconds, and then it was rejected, right? So I think we can be sure if you look at the audit event for it. If you go to the audit event, there is an audit annotation for the latency tracker, and you can see APF request timeout. It is very close to 15 seconds. So this proves that our request was in the queue for 15 seconds, and it was rejected by APF.
All right, so we have passed the first part of the API server's handler chain on the left. And now the actual quad processing happens. So now we have attached stuff to the context, we have validated, we have authorized all those things. But now we want to have a job, right? We want to create a job in the batch API group. So there's a multiplexer in front. It knows about all the paths for different resources. Among them, there's APIs, batch, V1 jobs, and there's a pipeline for the actual request processing behind, and for each of them, the thing exists. Most of them are very, very similar, so there's a generic registry implementation, it's called. We see it in a second. And one of those is for jobs here, it's the first one. So let's look at the pipeline for jobs. We create a V1 batch job, and V1 is a GA version, and one could imagine there's just V1, but in the past there was a V1 beta one, for example. And versions are everywhere here, and we annotated the path of the request in this picture, and you will find something. I mean, V1 beta 1 is gone because we are GA for a long time, but there's still this int, and int stands for internal. There's an internal version, internal representation, and it looks very similar to V1, but it's an internal Go type. It's another Go type in the implementation. And yeah, you see there are transitions from V1 to internal, and if you call auto admission, for example, it's translated back to V1, and the same happens when you write to etcd. So lots of transitions, and when V2 is introduced at some point, then there are even more transitions, more conversions. So conversions is important. Conversion is a lossless transformation, and they are just about representation of the job object, but basically just a different shape. It's the same data, just represented a bit differently. It's lossless, and you can transform between all of them without losing any data, and you get back the same object when you go back the transformation. And there's also one transformation going to etcd, and we will see it in a second, which translates to the storage version. Jobs are stored in V1, but this doesn't have to be. They can be very different. And eventually, marshalling happens, and we write to etcd, and a job is an internal, a native resource. We use protobuf for that by default, but it can be JSON. A CRD is stored in JSON, for example. All right, so this is a picture, and another super important concept you find everywhere in Kubernetes, and if you have written controllers, for example, you will also encounter the scheme. The scheme is basically this very central registration object, and it knows about all conversions, all Go functions which convert. It knows about the kinds, group versions. It connects them to the Go type, which is associated to that. So basically, all the knowledge about the type system is encoded in the scheme. And attached to that is a codex construct, which knows how to unmarshal, marshal to JSON, to protobuf, and knows how to call conversions. All right, so let's look at the first phase. So we have the request, has a body, there's a binary blob, so the JSON here in our example coming from kubectl. Our context is completely filled. We know the user, we know the audit event, request info, everything. We know from the header it's JSON, so we call the codex data structure, decode that thing, and create a Go object batch V1 job. And after creating that, we call a defaulting function, which adds some fields the user, ourselves in this case, haven't added to the manifest. Right? You didn't specify all of them, so the defaulting makes sure those things are set. That's the first phase. Now we have a Go object, a V1 Go object. But you have seen here there's an internal type, so we have to convert to internal. So there's a converter. Converter is registered in the scheme, so it's called, and we have the internal object. And if you're interested into the code here, there's a package. It's deep in the kube repository. It's not exposed in the API package, but it looks very similar to the V1. And then we have a concept called registry. This is really the logic of quad. what is implemented here. Create, delete, update, all those methods. And there's a strategy for a job. And the author of the job resource can add things they want to do during create. So it's another defaulting phase. And if you know feature gates, you can enable feature gates, and then certain things can be set. If they are disabled, you can't set them, right? You can give values, but they're just dropped during processing. And these kind of things happen here in the prepare for create. Here in the example, I looked into the job resource, and yeah, it set some fields. So the pod failure policy is a new thing, it seems. This is set to the default value here. Then validation admission happens. Everybody of you will have experienced that. There is mutating admission, so you can add webhooks. There's an admission chain here, and you can add webhooks. You can add cell policies. There's an alpha feature for that. And of course, it can go wrong. Then you get this 422 unprocessable entity for all of them, actually. Then there's an API validate phase. This is Go code, again, in the strategy here, in the create strategy. It checks like the name that it's proper as expected, and the fields have the right values. And then admission is called again, and admission might call your webhook, does other things, checking for namespaces, for example, checks the CL rules. And then we are basically, yeah, we are ready with a validated object. And now we want to store. Now the interesting bit comes, we want to create an object. So this means write to etcd. So what happens here, we have the batch object, and we translate that to a key for etcd. etcd is an key value store, so the key is registry, jobs, foo is the namespace, pi is the name of the object. Then there's another registry function, prepare object for storage. Super boring, it just overrides it wipes the resource version, because the resource version is stored in etcd in a different way. Then we call the codex again, so this time reversely, we encode, so we convert our internal object to v1. And then we have a Go object, and then marshalling happens because we want a JSON object, because the accept header says JSON. Oh, no, sorry, I'm too fast. We are storing here in etcd. So it's about the storage version, and we know jobs are stored in proto, so we get protobuf here. KMS encryption is the last step, a binary transformation. So if you want to encrypt, this happens here. And then the etcd client is called with an optimistic put. And optimistic means everything we have done before, like all the 20 minutes before, they were optimistic. Like we hope that the put will succeed. And as you know, when you create, you might get it already exists, and this is an error the etcd client returns when the key already exists. And if it exists, it's translated in this 409 error and returned to the client. We are nearly finished, so etcd is updated, but we want to tell something about the success to the kubectl. So we take again the internal object here, the batch job, the Go object. We convert it back to the request version, which might differ from the storage version. Here it doesn't, it's both v1. We encode according to the header here. There's an accept header attached to the request. We encode, we write it to the response writer. And basically, yeah, the pipeline is done with that, right? And we are nearly finished with the API server processing of this request.
Yes, and as these steps are being executed, the audit event in the context are being updated. And then it's time for the request to leave, but not just yet, because the handler chain are already in the stack. So the request goes through the handler chain, but in reverse order. And at this point, the audit handler has a chance to persist the audit entry, the completed audit entry, using the backend, and usually it's a log file. Also, the HTTP log handler has a chance to flush the HTTP log entry to the log, and so at this point, the handler chain is complete. It returns, and then the HTTP server resumes control, and it sends a reply to kubectl. So depending on the reply from the server, kubectl may have more steps to do. For example, if kubectl receives a network error and the request is read-only, it may retry the request. Or if kubectl receives a response and the response status code is 429 or 5xx and it has a response header named retry after, it will retry. So client Go basically is the official client for talking to Kubernetes cluster, and it has this built-in retry logic built into it. And if we build our application using client Go, our application will automatically retry on our behalf. So in our case, the request was successful, and the kubectl completed the request, and we see a response that the job was created.
Yeah, and with that, we have hopefully passed our interview question, and I hope some of you have learned something about what happens really when a kubectl is executed, kubectl create in this case. Of course, every box deserves its talk in its own, right? There's lots of stuff behind. So if you have questions, of course, ask them. I think we are out of time. I'm not sure whether we have time to the next talk. Yeah, we are here. Otherwise, yeah, so the usual channels. There is this code here, so if you have feedback, this goes to the scat page. Please give feedback, bad or good, anything you want to tell us. Yeah, that's all I wanted to tell. Thank you.
Thank you.